All set, and here we go. Let me start today's session by sharing a small experience with all of you. And this is particularly associated with all the core mechanical and civil engineers. So whenever you guys see a point loads acting on a beam, the beam could be overhanging or a simply supported beam, you are very much confident in terms of calculate the reactions at the supports. Yes sir, we can do it. But the moment you see a uniformly distributed load like this one over here or this one for the entire span, your confidence fades away, isn't it? Or when you see a uniformly varying load like this is a perfectly right angle triangle. Okay, what you have over here, zero load at point A, the load slightly increases, okay, at a certain distance from A, and then it keeps on increasing. This is what you call a uniformly varying load. Whenever you see this, you get nervous, right? Now it is going to be my responsibility today to make sure that whenever you encounter such loadings, UDL or UVL, you will never get nervous. You will stay confident, just like you stay confident with point loads, right? So good evening, students. This is Manas Patnaik, your friend and tutor, and let me set today's agenda. We are going to kick off by establishing how beams are defined. Secondly, we are going to take a look at the different types of beams, simple beams, simply supported beams, there are cantilever beams, there are fixed beams. We are going to take a look at that very, very briefly. And the most important aspect of today's class is going to be the loadings. You've seen point loads. Today, you are going to experience what exactly a UDL is, how UDLs can be converted to point loads. Okay, all of these things and much more coming up in today's session. We'll also see what exactly are uniformly varying loads. Again, how this entire triangular varying load can be converted to a single point load. Where is it going to act on the beam? All of these things will be discussed. It is going to be a fun ride. Okay, so if you've joined, don't go away. Watch this video right till the end, and I'm sure, let me guarantee you that your confidence level will go notches high. Okay, and then we also will be taking up some examples such as this one based on a uniformly distributed load. And I know a lot of you have problems particularly with uniformly varying loads such as this one. Watch this. This is a uniformly varying load. Now, how to calculate the reactions at A and B? This is something that a lot of students are struggling with. Okay, and you also have seen such kind of questions where this basically this is not a triangle, this rather looks like a trapezium. You can also say, sir, this looks like a combination of a rectangle and a right angle triangle. That's perfectly true, right? So it is my duty today to guide you how such problems can be analyzed with ease, with perfect simplification, right? So let me start today's session with the first agenda, that is, what exactly is a beam? You know what a beam is. It is simply a member in a structure. How is the structure made? Structure is made up of vertical members, which are popularly known as columns, and horizontal members, which is made up of beam. Okay, columns are everywhere in your room. These are vertical members, right? Then the floor above, this is what? Okay, it's a beam, right? When we speak about a beam, always remember this over here. This basically is a bridge, right? And it's an I beam over here. This is the longitudinal dimension, and this is the transverse dimension. The longitudinal dimension will always be very, very large than the transverse dimension. That is also one of the criteria of calling that structure a beam, right? It is acted upon by several transverse load. Why do I call transverse? If you're standing over here, then the load will be acting in this direction along the transverse axis. That is why we call it a transverse load. So this was just a basic example to get us going as to what exactly a beam is. Always remember, it's a horizontal member and the longitudinal dimension is far greater than the transverse dimensions. Okay, where do the loadings happen? Along the transverse axis, you can say, right? So that's a beam. Secondly, let me just brief you through the different types of beams. We kick off with a simply supported beam. So a beam which is freely supported on a beam which is supported freely on supports. The supports could be a knife edge or a roller is a simply supported beam. In a simply supported beam, you'll see a knife edge and a roller. Secondly, you've got a cantilever beam whose one end is always fixed while the other end is free. The load could be anywhere. Right now, I have applied at the free end. That load could have been applied over here also, wherever you want. Okay, that's a cantilever beam. Thirdly, let us talk about a fixed beam. A fixed beam has both the ends fixed. Two walls, you can say. Okay, at A and B, you can clearly see, and there is some load over here. So if you remove these fixed supports, you have to replace them with appropriate reactions and twisting moments. Twisting moments as a concept will be covered in mechanics of solids, and there is a special chapter for fixed beams. Okay, these rather fall in the category of statically indeterminate beams. Okay, I don't think so this is a right class for discussing statically indeterminate systems. You just remember this is also a type of beam where both the ends are fixed. How the reactions are calculated, that is a different science altogether. You have to consider other conditions as well. This over here is a continuous beam, more than two supports, you can clearly see, right? And then you've got an overhanging beam, a beam with one or both ends extended beyond support. Either one end is extended beyond the support or both the ends are extended beyond the support. In this example, this is extended to the left of A. Also, it is extended to the right of A. Let me just go ahead and tell you the extension here that I am talking about is popularly known as an overhang. This is the general span of the beam. This is the overhang. This also is the overhang. I hope you got this. Okay, so these are the types of beams. Now let me talk about the most important aspect of today's session, which happens to be loadings. What is a point load? It is assumed to be acting at a point. This is the point where the load is acting. This is the point where the load is acting. That point load in this example could either be vertical. That point load could also be inclined. If the point load is inclined, what you guys need to do is very simple. You need to resolve that into components, one horizontal and one vertical. If this happens to be theta, then you can simply write this as P2 cos theta, and you can simply write this as P2 sin theta. I hope you've now got a very good idea as to how point loads can be described. If you want to make the free body diagram of this beam, that can be done very easily. Make the beam again, remove these supports and replace them with appropriate reactions. Here they are. This is a roller support, therefore one reaction. This is a hinged support. I think a dot would be better. Okay, otherwise it looks like a knife edge, right? So this is a hinged support, and wherever there is a hinge, you remove that support and replace it with a vertical and a horizontal. You can say that this over here is by, you can say that this over here is bx, and the resultant will be somewhere along this direction, right? We are going to call that reaction as RB. It's as simple. Now secondly, what we are going to talk about, students, is a uniformly distributed load. I want all of you to focus. Okay, watch, this is going to be very, very interesting. Uniformly distributed load. Okay, so far we have heard about point loads, and we know how to analyze them, how to decompose them into components. How do we analyze a uniformly distributed load? Watch. It is a load that is evenly distributed over a part or over the entire span of the beam, over the entire length of the beam. There are two examples which I have shown. In this example, as you can see, the beam is as much as 10 meters long. Let's say this beam is 10 meters long, and only on 3 meters of the beam you've got this uniformly distributed load. So over a part of the beam. So this is for a particular part or section of the beam. Secondly, this entire length of the beam, the entire span of the beam is covered with uniformly distributed load. So both ways it is uniformly distributed load. Now how do you analyze this? That is today's agenda, right? Now let me just show this to you. Here we go. And here we go. So I have replaced this roller support with one reaction, this hinged support with vertical and horizontal. And as far as this loading is concerned, what I can do is, you can clearly see that it's written 8 Newton per meter. Now how do you analyze this? 8 Newton per meter. What is this, sir? Okay. So UDL, let me write it over here. UDL and their magnitudes are generally written in this form: W Newton per meter. Okay, just take a look. What is this? So this is 8 Newton per meter. इससे हमको क्या समझ में आता है? How do we understand? What is the meaning of 8 Newton per meter? The meaning is very simple. For 1 meter length of the beam, the total load acting in the downward direction is 8 Newton. If for 1 meter it is 8 Newton load, then for 3 meters, okay, that means we shall multiply both the sides by 3. Then for 3 meters, the result is going to be very, very simple. It is going to be, for 3 meters, this is going to be equal to 8 3 is 24 newtons. So essentially, listen to what I say very carefully. So essentially, this entire UDL can be replaced by one single point load, which is having a magnitude of 24 newtons. Okay, and if you watch carefully, this shape over here, I shall use a red color, let me use pink. This shape perfectly resembles that of a rectangle. Yes sir, this looks like a rectangle. Where is the center of the rectangle? Sir, center is somewhere here, sir. So where is that center? Center is here. So if I were to replace this entire UDL with a point load, okay, that load will be acting at the center of this 3 meter span. The center of 3 meter span is 3 by 2. If this is L, it is going to be L by 2. So 3 by 2 is 1.5. So 1.5 either from C or from B. And we'll put a load of 24 newtons. That's the entire idea. Now let me remove this. Why shall I remove it? Let me place it over here, and here it is. 24 newtons. Okay, here it is. 24 newtons. 3 by 2 from C or from B. I hope you now have a fair idea about UDLs. Okay. Again, remember, in case of UDLs, the geometry that you see is that of a rectangle. And so why is the unit Newton over here? Why isn't it Newton per meter? As you said, this is Newton per meter and you multiplied 3 with it. The reason being very simple, students. You see, what we are basically doing is, this is 8 Newton per meter. We actually multiplied it with this 3 meters. So meter and meter will cancel each other out. And what we are only left with is this 8 Newton times of 3. And that happens to be 24 newtons. Okay. So whenever you are dealing with UDLs, that means you are dealing with rectangles. Simply use this formula, WL. Okay. L by 2 from both ends. Let me write it here. L by 2 from both ends. Now I'm sure you have a very good idea about UDLs. Take a look at this example. Take a look. Sir, this also looks like a rectangle. What is the span onto which the UDL is active? Sir, it is active on the entire span. How much is it? Sir, this is equivalent to 10 meters. Okay. So what is this height? Sir, this is 8 meters, 8 Newton. Okay. 8 Newton, 8 Newton, 8 Newton. That means in 1 meter, the load is 8 Newtons. So you can analyze it this way. So if in 1 meter, it is 8 Newtons, then, so we've got a span length of 10 meters. So for 10 meters, it is going to be, you simply need to multiply both sides by 10. For 10 meters, so this is going to be 80 Newtons. So what you can simply do is, again, okay, you see 80 Newton point load right at the center. That means 5 from both the ends. Here it is. Check this out. This entire UDL can be replaced by one single point load. Okay, which happens to be 8 multiplied by 10. Bole to 80, and that too L by 2. Again, remember, L by 2 from both the ends. Okay, so L by 2 either from this end, leftmost end, or L by 2 from the rightmost end. Now you got the point. Okay, 10 by 2, that is 5. UDL understood? I hope. I sincerely hope that you now have understood UDLs. Now let me talk about uniformly varying loads. Let me read this out for you. A load whose intensity keeps varying, that intensity could decrease or either increase, moving from the leftmost part of the beam or from the rightmost part of the beam. The point here I am trying to make is that the loading is going to change. Okay, increase or decrease, we're not going to be talking about it. It is going to change. So how do you analyze this, sir? In the previous case, what we actually saw this was 8, and here this height was 8, right? So, and you said that this uniformly distributed load looks like a rectangle, okay, where the length is 10 and the height is 8 Newton per meter, obviously. But this is a slightly different kind of a geometry. This is a right angle triangle. First of all, let us talk about this right angle triangle. Okay, the geometry here was that of a rectangle, sir, and we actually calculated the area of the rectangle. What you did, this 8 multiplied by 10 gave you the area of the rectangle, and you said that this area of the rectangle is the load, right? That is load 80, and it is going to act at the center, that is 5 from both the ends, and here it was 3 by 2, that is 1.5 from C as well as P. Okay, so yeah, here also you have to do the same thing. Just like calculating the area in rectangle gave you the one single load in this diagram, here also calculating the area of the right angle triangle. What is the area of right angle triangle? First of all, tell me. Area of rat. Why shall I write rat? Let me simply write triangle. It is the kind of triangle, isn't it? So this is going to be equal to, sir, this height, if we know, this height is W, and gradually see if we start walking from this point on the beam, as we keep on walking, we see the load keeps on decreasing, and finally at this point A, it becomes 0. Okay, so we start from W and we end up at 0 loads, right? For what is the length? So the length is L, right? So in order to calculate the area of the triangle, if this side is W and this side is L, it's very simple. It is going to be half of base. So base is L and height is W. So you simply need to use this formula WL over 2. We are going to replace this uniformly varying load by a single point load over here at a distance of L by 3 from the right and 2L by 3 from the left. The single most very important hint that I would like to give over here is wherever you see this 90-degree angle, from that 90-degree angles, the point load is going to act at L by 3. From that 90-degree angle, the point load is going to act, this point load WL by 2, that is the area of the triangle, is going to act at L by 3. Remember this. Okay, this 2L by 3 can be worked out. How? L minus L by 3 will simply give you 2L by 3. It's very simple, very basic. I hope you understand this. Okay. Now how do we proceed? You've understood this, right? Right angle triangles can be dealt. Again, half of base into height is what we are going to use. This entire UVL is equal to area of the triangle itself. This is how you need to place it. Secondly, students, what you need to do is take a look at this triangle. So here the height is W and the length is L. Let me zoom. So here the height is W and the length happens to be L. Again, the same concept. Even here, the area is going to be height of the half of base. Base is L, sir, into height. Height of the triangle happens to be W. So this also is WL by 2. If you encounter such uniformly varying loads, okay, you see an increase over here and then you see a decrease from 0 to maximum and then from maximum to 0. In such cases, remember, you can replace this UVL by a single point load over here. From the left end, it is going to be L plus A by 3. Let me zoom in. From the leftmost end, it is going to be L plus A by 3, and from the right it is going to be B plus L by 3. These are some formulas which I want all of you to remember, to memorize, right? Yeah, I think we can move ahead. And as far as this distance D, A is or B is concerned, this is basically the distance where the loading was at its peak or the loading was maximum, and that is W Newton per meter. Okay. Now, I think we can start solving the question. So the problems that I have decided for you is example 3, that is slide line. Let me now move to slide 9. Okay, there is slide 9 and here it is. This is it. Okay, watch, this is going to be interesting. Fun. Right, let me start with UDL and then I'll also be discussing 2 problems from uniformly varying loads, one of which is slide 11, this one, while the other is this one over here. Okay, looks like a trapezium. Okay, take a look. Let me start with a simple beam problem. We'll also be transitioning into compound beams. You'll see 2 beams, okay, joined with the help of a roller or connected with the help of a roller. So here we go. Take a look. Okay, so what are we supposed to calculate? Find the support reaction for the loaded beam as shown below. Okay, you need to find the support reaction. Simple, it's a very simple beam. Okay, a vertical reaction at A and a reaction at B. Let me make this beam once again. Right, and what I'll do is I'll simply replace this UDL. Watch. What is this height? Sir, this height is 20. Okay. What is this length? Sir, this length is 4. So 20 multiplied by 4 will give you, sir, 20 times of 4 is going to give us 80. So you can replace this UDL by a single point load of sir 80 newtons, where exactly between A and C, sir. Here, let me show this to you. I hope you understood this. Very simple. Okay. 4 multiplied by this 20 will give you 80. So 80 has to be applied over here at 4 by 2 from A or 4 by 2 from C. Done, sir. The rest is very simple. Now you simply need to apply the equations of equilibrium and calculate the reaction. Let me start with moment about B is equal to 0. So when you do moment about B equal to 0, this is the force and this is the perpendicular distance. So RA multiplied by 8 and clockwise, that's why negative. Done, sir? Yeah. Then 80 multiplied by again perpendicular drop through B. This is 2 plus 2 plus 2, 6. So 80 into 6, anti-clockwise moment, that's why positive. Any other force or couple left? So no other forces left. By the way, talking about RB, it passes through B and B is the point about which moment is going to be taken. So this moment is going to be 0 of RB. Okay, as you cannot drop a perpendicular. 60 kilonewton meter is the couple which is acting in a sort of anti-clockwise. So therefore use a positive sign. Okay, force and distances are included in this 60 kilonewton meter. Understand this. Solve it. This is what you get, RA. Secondly, sir, what we can do is we can go for summation Fy0 because there are no horizontal forces or reactions. So you don't have to think about that. When you do Fy is equal to 0, what you have is, sir, plus RA, then we have minus 80, then you have plus RB. So write it down. Write it down. Solve it. How can we solve it, sir? There is one equation and there are 2 unknowns, RA and RB. No, there are not 2 unknowns. You already have the value of RA. Plug it in over here. Then you have one equation. You've got one unknown and you can get the value of RB as 12.5. So confident about UDLs. All right. You'll also be very, very confident, let me tell you, about uniformly varying loads. What is the next example that I thought of? Kaun sa tha? Slide 11, example 4. This is interesting. Watch. So this particular example of a beam is where we see a point load of 10 kilonewton at 1 meter from A. And then we see actually a uniformly varying load, right? You can say from this very point over here until you reach here, you can see the load is gradually increasing. You just need to think about the area of the triangle. Area of the triangle is equal to the single point load which is going to replace this entire UDL. Where are you going to place it? Sir, L by 3 from the 90-degree angle. That is the funda which you need to use. Again, this is the funda which you will be using. Where is it? Remember, area of the triangle. This is the area of the triangle. Okay, and L by 3 from the right angle triangle. Let me start again. This is something that we've discussed. Let me move to this uniformly varying load problem. Let me make the beam again. Okay, sir. So I've recreated the entire beam, but I have not replaced this uniformly varying load with a proper point load. And where exactly do we need to place it? You see these points over here. Let me make the corresponding points. I'm making two diagrams because I can copy and paste and modify stuff on a PC. You guys can't. Okay, because you will be, I'm sure, doing this on a piece of paper. So take a look. 2 meters, 2 meters somewhere here. Okay. Okay, so what we can actually do is we can actually calculate the area of the triangle. Here it is. Sir, this actually is 2 and this height of the triangle is given as 15. So half of base is 2 and height is 15. Just do the math. This is going to work out as 15 kilonewtons. Lovely. And this is the 90-degree angle, sir. What is the span? Sir, the span is 2. That means 2 by 3 from this spot. 2 by 3 from here. 15 kilonewton. 2 by 3 from here. Here it is. Let me zoom in. I'm sure all of you saw this. Okay, so from this very point, 2 by 3, at a distance of 2 by 3, you've got this load, a point load of 15 kilonewton. This point load single-handedly has replaced this uniformly varying load. Easy peasy. Now let us go ahead with the moment equation. First of all, I'm taking the moment about point A, and let me start with RB times of perpendicular drop from A. The distance is 1 1 2 1 1 बोले तो 2 3 4 5 6 6 times of RB anti-clockwise. That's why positive. No, I did something else. Okay. First of all, for a moment I have taken this force. So 10 multiplied by this perpendicular drop. 10 times of 1 clockwise. And that's why negative. The second force I have dealt is, let me check first of all. Okay, 15. So this is 15, sir. And this is the perpendicular drop from A. Here it is. So 15 is the force creating a clockwise moment at A. And this distance, if you watch, this distance. Sir, this is going to be 1 plus this. Sir, how much is this? Here it is. 4 by 3. Okay. So let me write it down. Done. Okay, sir. And then we have to deal with this 10 also. So this is the force, sir. And let me drop a perpendicular on the line of action. This is the perpendicular distance. 2, 4, 5. 10 times of 5 anti-clockwise. That's why positive. Done. Okay. And finally, you have this RB multiplied by 1 plus 1 plus 2 plus 1 plus 1. Just do the math. Whatever it is. Okay. 6. Right? Since it is anti-clockwise, that's why you see a positive sign. So this is one single equation, one unknown, that is RB. Calculate. This is what you get. You can also use summation Fi equal to 0. Positive, negative, negative, positive, positive. Write them down with the proper signs. You already have RB. Put this value over here. Then solve for RA. This is what you get. 13.34 kilonewton. Understood how to tackle problems based on uniformly varying loads. But don't go anywhere. I've got one more problem for you. And this basically is going to be a combination of a UDL and a UVL. What you see over here is a UDL. Let me try and make this. And a UVL. Sir, where is the UVL? Let me show you. You guys are so innocent. This is a UVL. Okay, so this is a very beautiful question where there is not just one beam, but there are two beams. Okay, there is a beam AB and there is this beam CD. Right, both the beams are joined at or connected with the help of this roller, and there are separate loads. There is only a point load on the beam AB, And there is this sort of combined UDL UVL load on beam CD. How to analyze such cases is going to be our next agenda. Just watch. Very interesting case. Erase. And what I have basically done, okay, is I have created a rectangle and a right angle triangle. What? A rectangle shown in this blue color and a triangle shown in this green color. Okay, fair? Okay, sir. If you watch carefully, if you move from this point, at this very point, that is point D, you see a loading of 8 kilonewton per meter, and it gradually decreases until you reach here. It becomes 2 kilonewton per meter. It's a uniformly varying load. Okay, it could either decrease. If you are moving from this very point over to the right, you will see the load is going to increase, but the load does not start from 0. It starts from 2 kilonewton per meter. Right? And that is what I'm worried about. Now, how to tackle such cases? Watch, it's very easy. Sir, this, if I consider only this much portion, so this is going to be 2 kilonewton per meter, isn't it? So this is going to be 2 kilonewton per meter. And the remaining portion is going to be, sir, 8 minus 2. So this is going to be 6 kilonewton per meter. Very, very simple. And that is exactly what I'll mark over here. Understood? Yes, sir. Okay, I'll be making the entire free body diagram for both the beams, and I'll also be removing these supports and replacing them by appropriate reactions. Don't worry. We'll be taking care of all of those stuff. Now, just think about calculating the area of triangle. If you have the area of triangle, you've got the single point load, which is going to replace the UVL. If you've got single point load corresponding to this one, that can be calculated. Just a sec. This area is half of base. Sir, the base is, just watch, from here till you reach here, from C to D. Sir, the base is 3 plus 4. 3 plus 4 is 7. So half of base is 7, sir. And this height of the triangle that we have is 6. Is going to give you 7. 6 is 42. 42 by 2 is 21. Done. Secondly, as far as this blue triangle is concerned, this is going to be, sir, area of rectangle is simple. Length multiplied by breadth. So the length is 7 multiplied by breadth. This height over here is 2. 7 times 2 is 14. So again, these loads, UVLs or UDLs, can be replaced by 21 kilonewton and 14 kilonewton forces, point loads. But you have to place it in the right spot. Where for rectangle, you remember it is going to be L by 2, and for triangle it is going to be L by 3. Remember, with respect to the right angle, always. For rectangle it is L by 2, for triangle it is L by 3 from the right angle corner. And I've written all of these things over here. Okay, so this load of 21, half of 42, is at a distance of 7 by 3. Okay, 7 by 3. This 21 will be somewhere here, 21 kilonewton. For the green, and for the blue region, you have 7 multiplied by this 2, 14, exactly here, 14 kilonewton. So this distance is 3.5, and this distance is L by 3, that is 7 by 3. This is 2.33. I hope you've got this. Okay, now let me do this in a much more civilized sense. Here it is. Watch. 14, the blue rectangle that you saw, UDL, okay, at the center, half of 7, 3.5, 3.5. 21, the green triangle that you saw, right angle triangle, okay, so L by 3 from the right angle, L by 3 from the right angle, that is 2.33. Okay, I'm sure you can work out how these calculations have been done. This is 2.33 and this is 3.5. So 3.5 minus 2.33 will give you this. Now, sir, we are very much interested in creating the free body diagrams. Okay, free them. Free the bodies. That's a free body diagram. Remove these supports. Okay, and as you can see, there is a roller over here. So that roller is in contact with this point of the beam. It is also in contact with this point of the beam above and the one below. So you have to replace the ruler with appropriate reactions in the form of RC above and RC below. Done, sir. The next thing is remove the supports. That's a hinge. That's a hinge. Okay. Replace them with appropriate horizontal and vertical reactions, and that's a ruler. Replace it with a single reaction, and here we go. Done. As you can see, there is no horizontal loading. So the reaction that I have marked over here, since there is no horizontal active loading, the reaction is also going to be 0 in that direction along the horizontal. Same is the case over here also. Okay. Even if you go for fx0 for this beam CD, you still will get a dx is equal to 0. That's true. Okay. Now let me analyze the beam one by one. Let me start with beam CD. Okay. Straight away, I'm going to take the moment about d is equal to 0. So RC multiplied by perpendicular distance. So RC multiplied by this is 3.5 plus 3.5, that is 7. 7 times of RC negative. Why? Clockwise. Second, you've got this 14. So 14 times of perpendicular distance. How much is this? Sir, this is 3.5 actually. Plus 14 into 3.5. Then you've got, sir, 21. This is the force and this is the perpendicular dropped. How much is this? This is, sir, 2.33. So 21 multiplied by 2.33 is going to create an anti-clockwise moment. Positive. Okay. And trust me, after this video, I am sure none of you who are with me still is going to have any problem whatsoever as far as dealing with either UDLs or UVLs are concerned. Okay. You'll crack it. Don't worry. Okay. So far so good. Now what's up? Solve for RC. This is what you get. Go for summation Fy0. Positive, negative, negative, positive. Write them down with their proper signs. You've got value of RC as 14. Put it over here. Solve for RD. This is what you get. Done, sir. Very easy. Now take a look at beam AB. Take a look. So as far as beam AB is concerned, let me take the moment. You can take the moment about whichever point you want. I don't give a damn, right? This is the problem of statics. You can take the moment about any point, but I always pick those points which enables me to make my task easier. Okay, that means I have to deal with lesser number of forces. Sir, moment about B0. Force, perpendicular distance. So RA times of 3 plus 1 plus 1, that is 5. Clockwise, that's my negative sign. Okay, so 3 multiplied by 4 and then RC multiplied by 3. Both of them anti-clockwise. Let me write this in one go. Solve for RA. Go for summation Fy. Plus, minus, minus, plus. Write them down. Okay. You actually have the value of RA, don't you? That's why RA is 10.8. So plus 10.8. This is RA, by the way. Right? Simply solve for RB. This is what you get. So students, that was all from my side for today. And if you really appreciate the content, do share this video with as many students, as many people as you can, maybe in your WhatsApp or Telegram groups. Okay. What else can I say? In the upcoming sessions, we'll also be dealing with forces in the 3D space. That also is a very interesting chapter, and I'm sure that the concept of vectors is going to help you understand all of that in a much better fashion. Okay. So yes, that was all for today. And if you've got any doubts, do let me know in the comments. And if you want some other topics that should be discussed in the engineering mechanics class, do write them down in the comments. Okay, I go through all of them and I'll try to respond to all of them. Thank you very much. Good day. Take care.